What I will do is of course, there are other methods, we will come back to that. I just want to show you how you would fit trends in R using LM or another package. So, let me go back now to R. Increase the font size to Braille font. Okay. Now, what we are going to do is, let me actually maybe throw away all the variables here. Doesn't want to. Yeah, thank you. Okay. So, let us start a fresh session here. One of the data sets that exhibits trends is this very nice data set, which is the data set is nice, but the phenomenon is not so great, which is the carbon dioxide emissions. So, what we can do is let us actually load this data set. It comes pre-installed with your base packages, it is a CO2. It may be good, for example, to read up something on the data set. Of course, it is asking which CO2 you are loading. You can actually load this in the, I think it is loading from the TSA. So, it is a levels of carbon dioxide at Alert Canada, I think it is loading that. So, that is what it has done for me. If you are not sure, there are other, there is another CO2 here, but I think this is the, this is from a different geographical region. So, let us plot and see whether it has the features that we want. Okay, this is not the one that we want, well, it is okay, it has a trend and some oscillations, no worries. So, let us work with this data and see. The other one that is the CO2 that is present in the, I do not know if this will do it, oops, let us see if it works. I do not know if it will work, oops, okay. Not found. Or maybe I can just unload the TSC just to show you that it is a different data set, but that also has a trend. This is one of the confusions in R. So, I am going to actually unload. It's the same thing. Oh, maybe because CO2 is already loaded. Okay. Yeah. So, this is a different CO2. This also has the features that we want. It has this linear trend. I do not know how well you are going to see, you are able to see. Let me zoom out. So, this is the trend. You can see that it has this trend and then there are oscillatory features and then maybe it has some randomness in it. We are not able to see that at least visually. In the classical approach, you think of this series as being made up of trend plus some periodic component plus a random component. Now, as I said, there is a non-parametric approach that one can adopt and a parametric approach. First of all, this is a time series object. When we load CO2, I think you should be able to see that. Let us see. I want to close this. Okay. This is a data frame, you can see. Yeah, it is not a time series object, it is a data frame. On the other hand, if you were to go back and load the reload the TSA package and then get the CO2 from the TSA package, you get a nice time series object. Of course, you can always convert a data frame object to a TS object, it is not difficult. So, let us ask now. So, I am going back to the CO2 in the TSA package and it clearly shows it is a time series object. If you are not able to see that, there you go, it says true, and it has also the similar trend, but now this carbon dioxide emission is being recorded, has been recorded in a different geographical region over a different period of time. So, let us say we work with this, this also has a trend and a periodic component and so on. Now, let us say I want to fit a linear trend to this. The classic approach is to use the in R is to use the LM routine, where you fit a model of this form alpha series as alpha naught plus alpha 1 k. Now, if you have to do that, you have to first extract or construct the time series vector, because the regressor, the time stamp vector, sorry, the regressor here is a time instant itself. Okay. Now, that can take some time. First of all, it may be good to know when this was recorded. So, it was recorded in this period, as you can see, and it is a monthly CO2 data. How do I know that? Well, I can ask for the structure. As you can see, it has been recorded on a monthly basis from Jan to December, all months, and over these years from 1994 to 2004. We say that this is actually recorded on a yearly basis, but with a frequency of 12. So, the unit of observation is a year, you can think of it that way, but you are within a unit of observation, you are observing 12 times. So, that is why when you ask for the frequency, which is shown here, when you look at the attributes of the time series object, the third one, the first is a start point, second is a stop point, and the third is the frequency with which it has been measured. And it has been measured 12 times in a year, that is what it is telling you, all right. Now, as I said, if we want to fit a trend of this form, we have to construct a time vector, and that can be a bit painful. It is not difficult, but it can be a bit cumbersome. You might want a routine which looks into the time series object, straight away takes the data and the time stamps and fits a trend for you using the least squares method, and that is what the TSLM from the forecast package. You should install the forecast package. It is a fantastic package. It has a lot of nice routines in it. One of the routines that you will really love is a routine that automatically estimates the order of the ARIMA model for you. Okay. But do not get pampered by that routine, all right. Be careful, it does help. A lot of people say that they did find it useful, but they were also misled by it. Any automated method for order determination should also be used with caution, right. So, I have installed the forecast package, and it is also loaded into my R works environment. So, there you go, this is the forecast. The forecast package has a number of useful routines which we will use later on as well. Okay. So, let us actually use the TSLM. In fact, if you go to the routines available in the forecast package and pull up the help on TSLM, towards the end of this help file there is a simple example which generates a synthetic time series which has a trend plus sinusoid and a periodic signal, and your random component. Okay. So, you can see, I do not know how well you can see at the bottom here, but there is a first component is a regular one, and then you have the sinusoid component, and then you have a trend as well here. Okay. So, this is the first one is your random component here, R norm, and then you have the trend, linear trend followed by a sinusoid. So, that is put together. You can work through that example as well, but just let us look at the CO2 data here. Now, what we are going to do is we are going to fit a linear trend and obtain the results in a variable called fit. So, TSLM, and the nice thing is you can say here CO2. The formula here, if you recall, I have shown you the syntax of the formula LM. You use the tilde operator to express the relationship. The CO2 is a series for us, and we want to fit a trend, and here it is assumed that the trend, when you say trend, it is linear trend that it is going to fit. And whereas if you were to use the LM, you have to explicitly specify the regressors, for where the regressor here is k. Of course, you also have this constant, but that is automatically fit by LM for you. So, regressor here is k, With the LM you have to construct the time stamp vector and pass it on as a regressor. Here you do not have to do that, just ask it to fit a trend and it will do it for you. Okay. So, it has done it, and it is important to know what attributes this object has. So, it says that these are all the things that are stored in the fit, the coefficients alpha naught and alpha 1 for example, we can ask for that. So, there you go, the intercept term and the trend, right. Alpha naught is the first one and alpha 1 is a second, they are estimates of that. And what we are interested in is of course the residuals, right. We want to see if the linear trend has sufficed for this series. So, let us plot the residuals. There are other attributes as well, but we will not worry about that now. What do you think? Have you managed to get rid of the trend, right? But then what else do you see now? As expected, you see a periodic component. Now, I am going to talk about a generic approach to this. In general, there are other routines. For example, there is something called STL, a routine called STL, which comes with the stats package. It stands for seasonal trend decomposition, and it uses a method called LOS, but it asks the user, for example, to specify the seasonality. Okay, for that you should have some information a priori. Even in this, I could have asked, for example, to fit both the seasonal component and the trend component, or in other words the periodic and the trend. Okay. So, what do you expect to see if it has done a good job of fitting the seasonal component? You expect to see some random component like this, right. There is no particular trend or seasonality and so on. It has automatically done that for you, but when you have set season, what it has done is it has assumed that the underlying component has a periodicity of 12. That is, remember we said we are measuring, we have 12 observations in a year. So, it assumes that the periodicity, I have strictly speaking the observation interval is 1 month. So, by saying that the frequency is 12, it reads that frequency and it assumes that the periodicity is 12. Of course, you can specify, you can override that and say no, do not assume 12, there is some other periodicity as well. But how do you know what the periodicity is, right? That is the big question that generally goes that is unknown a priori. In certain cases you may know it, but in a lot of other cases you do not know the periodicity. One has to discover it through a data analysis, and that is where your spectral analysis comes handy, which we will introduce very soon this week. So, the spectral analysis allows you to detect periodicities, and one of the ways to detect periodicity is of course to look at the power spectrum of the series and figure out what is where the peaks are. Just to give you a preview, we will go over the theory, but a lot of you must be familiar with power spectrum. A power spectrum plot is a plot of power versus frequency, and we search for peaks in the spectral plot. At whatever frequency you notice a peak, you say well that component is present predominantly. Now, we will learn later a measure or a concept known as periodogram, which will do this for you. A periodogram is nothing but a power spectral density plot, empirical power spectral density plot, which plots power versus frequency, and there is a routine called spectrum in the stats package, but I am not so fond of that because it plots not the power but decibels rather, 20 log 10 of power, and I am not so comfortable with decibels and so on. So, I do not like the plot that it produces, and then you have to go through additional steps to make sure it plots only the absolute one. Rather than that, we can actually use in the TSA package, which we have already loaded, there is a routine called periodogram. Okay. So, just to make sure, yes, we have loaded the TSA package. We can ask, for example, with the first fit that we had where we only fit the trend. Remember, we noticed, going back to plots, we noticed, for example, this periodic residual when we only fit the trend, and now I want to know the periodicity. So, what I can do is I can generate the periodogram, or and let me zoom out here to show you how it looks like. So, what you see here is the power on the y axis and the frequency on the x axis, right, and you notice a peak. Do you notice a peak in the plot, right? There are other cousins to that peak, but they are kind of tiny, subdued, but the predominant peak is somewhere at, any guess? 0.08 roughly, and that happens to be 1 by 12. Okay. So, that confirms that there is a periodicity of 12 months, or in the sense 1 year, but in general they need not be the case, and you may have other harmonics as well, which this we call as the, for example, you can say 1 over 12, the frequency at 1 over 12 is a fundamental frequency, and then if you see there are 1, 2, 3 other minor peaks, they may be the true periodic components present in the series, they are not necessarily harmonics, or they may be mathematical artifacts, and we will talk about that later on, what we mean by mathematical artifacts. At the moment I see a clear peak of 1 over frequency 1 over 12 or period 12, and therefore, you can go ahead with the second approach. And now what you do is, what we have done is we have fit a trend, we have fit the seasonal component, and then we fit an ARMA model to the residual if we find that to be stationary. So, one has to go through the same procedure that we went through yesterday to build a model. As I said, there is another routine called STL, which does a beautiful job of decomposing this, and it assumes that the periodicity, again, if you just say S dot window, the seasonal window, that is one of the arguments in STL, where you have to specify the periodicity or the length of the smoothing window for extracting the seasonal component. When you do this, I am sorry, let us plot it. So, there is a very nice decomposition that it does, but it does not work all the time. However, it is a fantastic approach where it uses this non-parametric idea that we have discussed earlier. It does not fit a linear trend necessarily, it does not assume any polynomial trend at all. It is extracting the seasonal component for you, it is extracting the trend component of you for you, and this trend component is not obtained by parametric fitting, you should remember that. It is obtained rather by the non-parametric idea that I have talked about. Of course, it is not as straightforward as I have discussed. There is a more complicated method which we will not discuss in this course, but it is good to be aware of this method called STL. And now you can access the individual components. As you can see, the series is on the top, the seasonal component is on the second panel, the trend is in third, and the irregular component is in the bottommost panel. So, this is one way of doing it, but provided you know the periodicity, you have to supply that information to STL. Alright, so this is a general approach that you want to use. You fit, if you want to follow parametric approach, you actually use this TSLM or LM and fit a trend, whatever trend you feel is appropriate. For example, you can try this on the Swiss stock market index example series that we have looked at before, you know there is a trend and so on. So, you can ask, for example, here if you were to plot the sorry. So, this is a series we have. Here do you expect to a linear trend to do the job? No. So, then you have to fit a quadratic trend perhaps or maybe even a cubic polynomial, find it out what is the appropriate trend and see once you have removed the trend whether there is any seasonality, and if there is none, then that means you only have a trend plus this model. Okay. So, this kind of concludes what I wanted to show as far as the trend analysis is concerned or handling trend type non-stationarities is concerned. By the way, I said the forecast package comes with a lot of other routine nice routines. For example, there is something called TS display, right, and if we go back to our CO2, it generates some it not only produces a time series plot, but also it gives you the ACF and PACF straight away, right. The sample ACF and sample PACF are shown. And what do you notice in the ACF? It's definitely there is a periodicity and also that the decay is slow. Whenever you see such a phenomenon in the sample ACF, you should suspect some kind of a non-stationary effect of the mean type, either a trend or an integrating effect, right. And one has to of course distinguish between a trend type and an integrating effect, because in terms of the nature itself they are different. One is a deterministic type, other is a stochastic type. So, look through some of the other routines in the forecast package, and there are so many tutorials on the net. I strongly recommend that you go through for example, Quick R, do not get confused with Quicker. Okay. Quick R is a very nice website which has some very nice examples and demos. Okay. So, let us get back to the theory part. As I said, you can follow a parametric approach or a non-parametric approach, and there are other approaches in the non-parametric basket. One, as I said, is simple averaging. The second one, which is used quite frequently, is this so called exponential smoothing, all right. And the way this M is generated is using this kind of a filter, alpha times Vk plus 1 minus alpha Mk minus 1, and the initialization is done this way. So, you start off with M of 1 being V of 1, that means the first estimate is V itself. Subsequently, you apply this filter. We will show later on that this is indeed a filter when we understand what is meant by filter, how to analyze the filtering characteristics of a filter and so on. We can come back to this exponential smoothing equation and see what kind of a filter it is. And the other option is of course to use some smoothing by elimination of high frequency components. Essentially it amounts to applying some filter, and you can apply, there are so many filters available in the literature, and you know, if you come up with your own filter you can name it after yourself also, that option still exists. But the bottom line is you want to carry out a spectral analysis of the data to be able to get a feel of whether there are periodicities, what kind of frequency components are present and so on, and that will be the subject of our lectures for quite some time. But let us get done with this non-stationarity business. Now, the other approach of course, as I have said, is a method of differencing, which we also use in handling integrating effects. But in the method of differencing, the difference is that we do not necessarily estimate alpha naught and alpha 1. We just difference the series and then we find that the differenced series is stationary if the original one has a linear trend, but with non-zero mean. Again here I have here beta 1, actually that should be nothing but your, what will be beta 1 in terms of alphas? It is alpha 1. So, it should be alpha 1, but I have just kept it generic to show you that the differenced series has a non-zero mean when the underlying, when this given series has a linear trend. If it has a quadratic trend, you have to difference twice. But there is one problem, in fact this is wrong here, it should be 1 minus q inverse wk, I will make that correction. There is one problem with this differencing approach to handling linear trends. So, you have Vk as alpha naught plus alpha 1 k, plus Wk, all right. And what we are doing is we are differencing Vk, so that we have here alpha 1, but plus 1 minus q inverse Wk. So, what is shown on the screen is not entirely correct. So, what we have managed to do is get rid of the trend, but we have done something else. What is the side effect? What we wanted to do is we wanted to model V as a sum of these two components. In the earlier approach we fit alpha naught and alpha 1 and then eliminated it, and then we would obtain an estimate of W. But here we have eliminated it by way of differencing, and now we are left with not Wk, of course this is alpha 1, but apart from that you are left with not Wk but 1 minus q inverse Wk, right. So, you will be fitting a model essentially to this series. What is that? If Wk is an ARMA process, then 1 minus q inverse Wk, let us call this as W tilde, this part alone as W tilde. W tilde unfortunately has a 0 exactly at unity. Is there a problem? We have assumed Wk to be stationary and invertible. What about W tilde? It is not invertible. We have forcefully introduced a 0, okay, and that is the problem with the filtering approach itself. Remember this differencing operation, we are differenced here, right, this 1 minus q inverse. What we are doing is we are passing Vk through an operation called differencing, whose transfer function operator is 1 minus q inverse, and then we get this. We will show later on that this differencing operation is also a filtering operation. In fact, I do not know, some of you must be familiar that this differencing operation is a high pass actually filtering operation. In this case, in the earlier case we said we will eliminate the high frequencies to estimate the trend, but our goal is reverse here. We do not want to estimate the trend, we want to get rid of the trend. Trends are typically low frequency, they are slowly changing with time. So, therefore, what we are doing here by differencing Vk is we are actually removing the trend, we are using a high pass filter. When I take any signal and I construct a differenced version of it, it amounts to passing the signal through a high pass filter, because when I take the difference of 2 points, the rapid ones are highlighted. When I take the average of 2 successive points, the rapid fluctuations are subdued. That is why averaging is a low pass filtering operation and differencing is a high pass filtering operation. How do you know which is high pass and low pass? Well, you just have to look at the net end result and ask what is it that I have retained and what is it that I have thrown away. In averaging, I have thrown away or kind of subdued the rapid fluctuations and I have a smooth version. So, the low frequencies are retained and therefore, it is a low pass filtering operation, whereas differencing is an operation where I am highlighting the changes. When I look at the difference between two observations, that means I am highlighting the fluctuations, the rapid fluctuations. Therefore, I am allowing only the high frequencies to go through preferentially, and that is why intuitively the differencing operation is a high pass filtering operation. We will show this theoretically later on that differencing operation is a high pass filtering operation. So, this is completely in contrast to what we had discussed earlier, and unfortunately it is introducing a non-invertible 0 here, right. You cannot do anything about it. Therefore, when you have a trend, deterministic kind of trend, you should try and avoid using the differencing operation to handle that. Although differencing can mathematically get rid of the trend for you, like for example here I can go and plot that. So, diff routine in R constructs a difference series for you. So, if you look at the difference series, what has happened to the trend? It has vanished, correct? the only thing that it is left with is a seasonal component. So, we have managed to get rid of the trend, but underneath what we have done is we have introduced a non-invertible 0, and we do not want that, correct. We want to work with stationary and invertible. Stationarity is not compromised, but invertibility is being compromised, all right. So, one has to be careful, although the objective is to work with a stationary series, how you obtain the stationary series makes a big difference, all right. So, what we will do is when we come back tomorrow, we will complete this discussion and talk about methods of differencing in the context of random walk processes. There differencing is absolutely the way to go. I mean, if you know there is integrating effect, the differencing operation is one of the standard solutions. It does not introduce any spurious effects, but there also if you over difference, if you have integrating effect of the first order, then one differencing will get rid of the integrating effect. But if you go further, then you will again run into the same issue, and that issue we call as over differencing. So, a differencing approach has to be used carefully. You should know when and how much to use. So, we will complete the discussion tomorrow and then hopefully get started with Fourier analysis.